So take any one fixed h, one hypothesis I from this hypothesis class, and consider a Bernoulli random variable z whose distribution is defined as follows. We are going to sample pairs from the distribution D. Then we set this z to be 1 every time our model hi misclassifies our point that we drawn from this distribution D. Okay. Similarly, we also define zj to be 1 whenever our model misclassify this example j. Since our training set was drawn IID from distribution D, then z and zj's have the same distribution. We see that the misclassification probability on a randomly drawn example, that is the epsilon of h, is exactly the expected value of z, because we defined z to be a random variable that is going to take value 1 when you classify, when this model classify correctly and misclassify an example. So we can write it like this. The error of the empirical error of a model I will be simply the average of the values of zj, where j will go from example y to from example 1 to example n. Thus, this epsilon circumflex, the empirical error, is exactly the mean of the m random variables zj that are drawn IID from a Bernoulli distribution D. And here, the distribution D will have the mean epsilon of hi for that specific model hi. So now we can apply the Hoeffding inequality, and we will say that the probability that the estimated empirical error to be far away from the real, the mean error, which is the generalization error, is upper bounded by this expression, which is 2 times the exponential of -2 gamma squared times m, where m is the number of examples. So this expression shows that for a particular hypothesis hi, the training error will be close to the generalization error. So this epsilon circumflex will be close to the epsilon, which is the generalization error, with high probability, assuming that m is large. So what we're saying is, if we train a model hi with, for example, 10 examples, 10 training points, the probability that our estimation is close to the real error of that model will increase if instead of training with 10 examples, we train with 1,000 examples. So by increasing m, we will reduce the difference between the estimated error, the empirical error, and the real error of that model. So let AI denote the event that this is happening, that let's say the difference between the empirical error and the generalization error is greater than gamma. We have seen that for any particular AI, it holds true that the probability of this AI happening is at most 2 times this expression here. Okay, so we simply replace this expression by AI. And remember the union bound, we have that the probability that this is true equals the probability of the union of all the events A1 to AK, where K is the number of hypotheses. We know from the union bound that this is less or equal to the sum of the probability of each of the events happening. Remember here, each of the events happening make reference to each of the hypotheses of our hypothesis class. So here we say for any hypothesis in our hypothesis class. And this is simply 2 times the exponential of -2 times gamma squared m. And this can be written as 2 times k, the exponential of this same expression. And from here, if we subtract from 1 this expression here to the left, and we do the same with this, we see that first, by subtracting 1 from here, what we're saying is simply, here we have for any h, we simply negate this. So saying that for no any of the h in this hypothesis class, which is, in other words, is the same as saying for every h in this hypothesis class. And if we do the same with the right side of the equality, this is 1 minus 2 times k, the exponential of -2 gamma squared m. We'll have this 1 minus 2k and so on. So we have then this expression where we are saying that the probability, with probability at least 1 minus 2 times k exponential of -2 gamma squared m, we have that the generalization error will be within gamma distance of the empirical error, the error with the training set, for all h in our hypothesis class. So at this moment here, we are saying that for every hypothesis in our hypothesis class, and remember that this analysis was done on the assumption that we have a finite class of h, we are saying that that the probability, with a probability at least of this number here to the right, our empirical error will be close to the generalization error. And this will be true for every hypothesis in our hypothesis class. This is called a uniform convergence result, because this is a bound that holds simultaneously for all hypotheses in our hypothesis class. Okay. Given gamma and some new constant, delta, also delta, we are assuming that is a positive number. How large must M, the set of training set, must be to guarantee that with probability at least 1 minus delta, the training error will be within gamma distance of the generalization error. So we are replacing this expression here by delta, and we are considering M training examples. We see that M is larger or equal to this expression here, where this delta is this expression. And then with probability at least 1 minus delta, we have that the distance or the difference between the estimated error and the real error is at most gamma for every h in our hypothesis class. So this bound tells us that how many training examples we need in order to make a guarantee. And we see that the training set size M, so the number of training examples, that a certain method or algorithm required in order to achieve a certain level of performance is also called the algorithm sample complexity. Okay, so here we can see this equality saying here m is the number of examples, and this is going to be larger than the some expression of the logarithm of k, where k is the number of hypotheses in H. Okay, so as you remember, this logarithm, what it's telling us here is that as you increase the number of hypotheses that you are evaluating, the number of examples that you need to train this model will increase only logarithmically. So you can increase this very fast, and m is not going to grow in that same rate. So the key property of the bound above is that the number of training examples needed to make this guarantee is only logarithmic in K, the number of hypotheses in H. Similarly, if we fix m and delta and solve for gamma, we get that with probability 1 minus delta, we have that for all H in the hypothesis class, we see that the distance between the estimated error and the real error will be bounded by some expression of the logarithm of K. Okay. So let's define this H star to be the hypothesis, the argument that will minimize the generalization error. So this is basically, this H star is the best possible hypothesis in our hypothesis class, since we are saying that this minimizes the generalization error. This is not the empirical error. This is the error in general. So we have this result here, that the generalization error of the H circumflex, remember that this H circumflex is the best hypothesis that we can find for our data set. This error will be at most equal to the error, the empirical error of the best hypothesis in our data set plus some gamma. And we can get to this expression by moving to the right side of the inequality, this here. So we saw this in the previous slide. Okay, so by moving this to the right, we get this expression here. And one point here to notice is that once you have this expression here, you can simply say, okay, this expression is less than this one, or most is the same, because the hypothesis, the best hypothesis with our training set, the error of that hypothesis, the only thing that could happen is that the error of the best hypothesis will increase, because this hypothesis will consider all the possible examples that can be drawn from the distribution D. That's why we are saying that this expression is less than this. This is the error with the hypothesis for every single point that can be generated from the distribution. And this is the hypothesis, the best hypothesis for a specific finite set of examples available as training examples. That's why this is going from here to here is true. And then here we see 2 times gamma, and this is true because we know that the empirical error of the best hypothesis is less than the generalization error of this best hypothesis. When we go from here to here, what we're saying is here, this is calculated only with our training set, And this epsilon is calculated with every possible, or we are making reference to every possible example that can be drawn from our distribution D.